All right, guys, we're going to get into some specific terminology when dealing with some certain situations. So what we're going to learn about today is two things. We're going to learn about something called a union of two sets, and that's basically just an or statement. And we're going to learn about an intersection, which is essentially an and statement. Okay? So we're going to have a lot of situations where we ask ourselves, what's the probability of this happening or that happening? Or we might say, what's the probability of one thing happening and another thing happening simultaneously, right? So we need to have kind of a process that is familiar for how to deal with all of these situations. Now that we're familiar with set theory, we can start organizing our thoughts and our drawings in set notation. So we've got marbles, and they're labeled 1 through 7 in a bag. So that means we have 7 marbles in a bag. The set S is defined as the set of all outcomes when one marble is pulled from the bag. So what could happen if we pull one marble from the bag? Let's define set S. We could get a 1, or we could get a 2, or we could get a 3, or we could get a 4, 5, 6, or 7. So set S looks like this. Let A be the event of pulling an even number, and B be the event of pulling a prime number. Okay, so these are subsets. So we've got a subset A, which is the event of pulling an even number. So what are our even numbers that are in set S? Well, we've got 2, we've got 4, and we have 6. All right, so those are all the even numbers in set S. And then B is the event of pulling a prime number. So B, what are all our prime numbers? Let's not be fooled here. 2 is our first prime number. Then we have the number 3. Then we have the number 5, then we have the number 7, and that's all the primes in this set. Okay, so we've defined those sets. So remember that A and B are subsets of S. And just like what we did yesterday, we should be able to construct a Venn diagram to represent set S. So make sure that we draw a big rectangle for S, and then we're going to draw a Venn diagram inside of S. So you guys should pause the video and try to do this on your own and then check with me to see if you're right. So I'm going to show you guys what this should look like. My Venn diagram in here, I'm going to have one circle to represent A, one circle to represent B. I'm recognizing that these two things could intersect. There might be some elements that are in set A and are in set B. Remember yesterday when we did this, we made one of our circles much smaller. And that was because we could see that visually one of our sets was much smaller than the other, but in this case, they're pretty similar. So that's why I'm making these circles pretty much the same size. I don't need to waste space. I'm just going to have them be similar. Okay, we're just going to go element by element. The element 1 is in set S, so it belongs in this box, but I don't see it in any of these. So I'm going to put the 1 on the outside. The number 2 is in all 3 of our sets. So it goes inside the box, and it also goes inside of both of our circles. I see the number 3 in set S. I don't see it in set A, but I do see it in subset B. So I'm going to make sure that it goes somewhere where it's within S and is within B, but is not within A. 4 is 1 through 7, and it is even, but it is not prime. 5 is within 1 through 7. It is not even, and it is prime. 6 is an even number within that set. And 7 is prime. So this is what our Venn diagram should look like here. Hopefully yours ended up looking just like mine. So what can we do with this Venn diagram? Well, it's helpful to have this available to you because in a lot of cases, looking at the Venn diagram is going to be the best way to visualize how to calculate things like this. What we're going to do first is I'm going to make sure that we understand what this is actually asking. So this says to calculate a probability that we've never really seen before. And what that says is the probability of A union B, which, as we defined above, is really just an OR statement. So this is the same as the probability of A or B. And next to union, I'm just going to draw that union symbol to remind myself that that's what a union is going to look like. Okay, so let's figure out what the probability is of picking a number from set A or picking a number from set B. Well, when we calculate a union, we're going to be able to count anything that's in either of these. So I'm just going to highlight what counts here. This union defines anything that is in A, so any of these things, those all count. They also count if they're in B. Don't worry about this because this point right here, this 2, is in A and it's in B, and that's okay because it covers at least one of these two bases, right? This number is in A or B. It's actually in both, so that's fine. All right, so what is that probability? Well, we're going to use our same formula, the number of possible outcomes. So what are the number of possible outcomes in set S? There are 7 of them, numbers 1 through 7. And how many of them are in either set A or are in set B? So we've got 1, 2, 3, 4, 5, 6. 6 of them. So the probability of A union B is 6/7. Okay, now let's do the same thing with what we've got over here. This actually says A intersection B. And as we defined above, intersections are just AND statements. So I'm going to make sure that I write down what my symbol would be for an intersection, remind myself in the future. So the question that's really being asked here is, what is the probability of picking an element of set A and of set B? So we want something that's in both, right? Well, where will we find something that's in both set A or set B? You'll always find those things right here in this overlap. Those are the pieces that are in both set A and set B. So if I want to know the probability of picking an element of set A that is also in set B, I still have my total number of possible outcomes that has not changed, 7. And of those 7, there's only one of those elements that is in both. All right? And the last thing that I want to talk about here, and I'm going to set this up for you and then ask you to answer the question. This says, why isn't the probability of A union B equal to the probability of A plus the probability of B? And here's why that seems like it should be the case. So I'm just going to write this out. Let's say that it is. Okay, let's say that's a true statement. We're just going to take a look at our picture here. Union is an OR statement. So we're saying, what is the probability of selecting something that's in either A or is in B? All right, so logically, some people might think, well, if I need it to be in either this set or in this set, why don't I just add together all the elements of A to all the elements of B? So let's do that. I'm going to do that right now. In order to calculate the probability of A union B, let's just figure out what the probability of A is. Well, the probability of A, it's going to be out of 7. How many elements are in set A? 1, 2, 3. So the probability of picking an element of set A is 3/7. All right, now let's figure out what the probability of picking an element from set B is. In set B, if I wanted to find the probability of picking an element of set B, it would be 1, 2, 3, 4/7. 4/7. Okay, we calculated this earlier, this probability of A union B. Right? We did that. So if this is a true statement, then 6/7 equals whatever this becomes on the right-hand side. But that actually ends up being 7/7 or 1. This is an untrue statement. So it's up to you to tell me why you think that is, and we'll talk about that at the beginning of class tomorrow.